So we wanted to show that using the idea of the connected sums, the Euler characteristic of this surface with two holes, which is denoted by, let's say, x hash y, where x, let's call this one x and this one as y, this is equals to the Euler characteristic of x plus the Euler characteristic of y minus 2. This is the thing we wanted to show. Now, as I mentioned before, that I can take this x and y, these two donuts or torus, and I can remove, let's say I can remove a triangle from here and a triangle from here, and then I can join them using a triangular cylinder, or so to say a prism that looks like this. So I'm joining them with this. Okay, so the idea to show this relation is lying on the fact that we can compute the difference between the Euler characteristics of these two topological spaces. So we want to compute the difference. So we want to compute the difference. Let's call that difference as delta chi, which is denoted by chi of x hash y minus chi of x plus chi of y, right? And obviously this x hash y, that is our new topological space that was generated from these two torus, it will have vertices, edges and faces, right? Because we want to compute the Euler quantity, those are the things we need. So I can say, let's say this is the vertices v1 minus the edges plus the faces, right? Similarly, for the x, I can write v of x, that means the vertices of topological space x, edges ex and faces f of x, plus v of y, the vertices again, the edges again and the faces again. So we see that this quantity is ultimately nothing but v1 minus vx plus vy minus e1 minus ex plus ey, and ultimately the faces as f1 minus fx plus fy. So this is just the difference between the vertices minus the difference between the edges plus the difference between the faces. So all we need to do is to compute the difference between the vertices, the difference between the edges and the difference between the faces. That is, by difference I mean how many of these vertices, faces or edges are we adding and removing. From there we can compute the difference, and once we compute the difference we can plug those numbers in this equation to compute the difference, and by our claim it should be minus 2, and we're going to see how we can do that. So again let me draw the figure. So this is where we removed the triangles, right? And we added the triangular prisms, or so to say triangular cylinders. So at first we want to see how many faces are we removing. So this is a computation for the removal of the I'm calling it a removal calculation. That means I want to compute how many vertices, edges and faces are we removing from the toruses that we had initially. That means the two of the toruses, right? So this is one, the guy called X, and this is the guy Y. So if I remove a triangle from here and I remove a triangle from here, you can see that for X we are removing one face, 3 vertices, and 3 edges, right? Similarly for Y, we are removing one face, 3 vertices, 3 edges. So in total we are removing 1 plus 1 is equals to 2 faces. We are removing 3 plus 3 vertices, that means 6 vertices, and we are removing 3 edges, so 3 plus 3 from each of these toruses, so 3 plus 3 is 6 edges, right? So this will be there. Now when we add these two with the triangular cylinder, we are adding vertices, edges, and faces, and we need to compute that as well. So this time we are going to focus on how many edge, face, and vertices are we adding. So this is the adding computation. This is what I'm calling it. So again, draw them, but this time they already has this slots, the triangles that were removed from the surface of the torus. And now we're adding a triangular cylinder like this, right? So notice when you add a triangular cylinder like this, what you are essentially doing is that you might think that, you know, there is this face over here, right? But that's not the case. Similarly over here as well. So let me use the green color to indicate that. You might think that you are adding the missing faces, but that's not what's happening. And let me give you a reason why. Think of a box like this, a 3D box, but from here there's a pipe. Okay, let me try to draw it properly. A pipe like this, and it connects to, let's say, a sphere like this. So do you think there will be a face over here? The answer is no. Why? Because it's just the way the box is. One of the faces of the box is actually generating this guy, so there is no face over here. The only faces you are adding is coming from these sides of the triangle. Let me draw them, and then I can explain. The only faces that will make a contribution is this guy, and the other one over here. So essentially when you are connecting a triangular cylinder, you are adding only 3 faces. Okay, so we are adding 3 faces. Then let's try to count the vertices. The vertices is easy. This is 1 2 3, 1 2 3, right? So we are adding 3 plus 3, 6 vertices. And what about the edges? We are adding these 3 edges over here, and these are 3 arms as well. So in total 3 plus 3 plus 3. So we are adding 3 plus 3 plus 3, 9 edges. That's great. We are done with counting how many edge, face, and vertices we are adding and removing. Now we just need to use this result over here. with this result. This will facilitate our computation of the difference. So the difference between the vertices is just the addition of vertices minus the removal of vertices. Because if you consider adding as a positive thing, then removal would be a negative thing, right? So that's why you put a minus sign over here. So addition of vertices is 6, removal of vertices is also 6, so this is just 0. Del V is 0. Similarly, the difference between the edges is addition of the edges minus the removal of the edges. So you are adding 9 edges and you are removing how many edges over here? I think it was 6. Yes, you are removing 6 edges. So 9 minus 6 is just 3. Finally, the faces. We removed 2 faces, right? And added what? 3 faces. So we added 3 faces and removed 2 faces. So this is just 1. So finally, the difference between the Euler characteristic is del V minus del E plus del F. And this is 0 minus 3 plus 1. And this is minus 2, right? But what was del chi? I think I called it x before. Sorry about that. It's chi, not x. Del chi was chi of x connected sum with y minus chi of x plus chi of y. So chi of x hash y is equals to chi of x chi of y minus 2. Proved. You can also even further compute this, because you know this x was what? A torus, and we know from our previous lectures that this is just 0. The Euler characteristic is 0. Similarly, y is also a torus. Its Euler characteristic will be 0 as well. So this is just 0 plus 0 minus 2. This is minus 2. And if you recall that I made a comment that, so that was a comment, so recall that what I said is that if a surface has a genus G, then the Euler characteristic of that surface, which is denoted by the following: chi of sigma of G. So this sigma of G means a surface with genus G. Okay, then the Euler characteristic of that surface with genus G will be given by 2 minus 2G. And this is true in this case, because look at our connected surface. It has 2 genus, 1 and 2. So if I use this formula 2 minus 2G and I put G equals to 2, I get 2 minus 2 times 2, which is 2 minus 4 minus 2. That agrees, right? Now you may ask, is there any way to prove this 2 minus 2G? Because I've been saying it a lot. And I can show you a proof, and we will see that very soon. And that proof will use the idea of this connected sum. So let's now try to prove it.